Konganadu College of Engineering and Technology.
Sunshine is a welcome thing. It brings a lot of brightness. Now I like to call upon Mr. T. Karthikeyan, Assistant Professor, Department of ECE, to welcome this gathering. Please, sir.
So, very good morning, participants. I would like to welcome Dr. PSKR Periyasamy, our Chairman, Konganadu Educational Institution, and I like to welcome Dr. R. Ashokan, Principal, Konganadu College of Engineering and Technology, and I welcome to today morning session resource person, Dr. S. Kumaravel sir, Associate Professor, Vellore Institute of Technology, Vellore, and like to welcome Dr. M. Dharmalingam, HOD, EC Department, and I like to welcome all the faculty members and students of the Department of ECE in Konganadu College of Engineering and Technology. And it's immense pleasure to welcome our participants from various institutions for 2 weeks online faculty development program on emerging trends and challenges in VLSI mixed signal processing for 4th industrial revolutions. So once again, welcome to all.
Thank you, sir. If your actions inspire others to dream more, learn more, do more, and become more, you are a leader. Now I like to call upon Dr. P. Ilayaraja, Associate Professor, Department of ECE, to deliver an inaugural address. Please, sir.
Very good morning, participants and resource person. On the behalf of Department of ECE from Konganadu College of Engineering and Technology, it is my sincere thanks to express regarding the funding provided by the AICTE for 2 weeks online FDP program. And at the same time, we want to express our heartfelt thanks to our management as well as principal for providing the space for conducting such kind of wonderful FDP program. Totally, we have received 120 registration response from the participants from various part of this country, and I express my sincere thanks to all the participants for their contribution. This FDP phase 1 starts from February 8 to February 20, and each day we have a 2 session, morning as well as the evening. So morning sessions begins exactly 10 to 12, and afternoon sessions 2 to 4. Each day we are having a feedback session as well as the attendance. So I request all the participants to provide your valuable feedback as well as the attendance. So this will be mandatory for getting the certificate. At the end of the day, we are having the online test. That details we will announce you later. So once again, I thank the AICTE as well as the management of Konganadu College of Engineering and Technology, principal and department heads, and faculty members and student coordinators for this wonderful FDP program. Thank you.
Thank you, sir. Every thought you produce, anything you do, it bears your signature. In this way, now I like to call upon A. Girija, third year ECE, to give a short intro about our resource person, Dr. S. Kumaravel.
It's the province of knowledge to speak, and it is the privilege of wisdom to listen. I feel overjoyed to welcome and introduce today's resource person, Dr. S. Kumaravel, Associate Professor, Vellore Institute of Technology. He did his bachelor degree from Government College of Technology, Coimbatore, and postgraduate degree from SRM Ishwari Engineering College in VLSI Design, and also he completed his doctorate in NIT Trichy. He worked as an associate professor at VIT. Presently, he is the head of Micro and Nano Electronics Department. He also has a work experience as maintenance engineer, junior project officer, lab engineer, and research associate. He is very much interested in mixed signal circuit design, RFIC design, and low power VLSI design. He successfully fabricated integrated circuits. He also published papers and his research works in IEEE conferences. I hope this session will be fascinating for you. Let me hand over the session to today's resource person, Dr. S. Kumaravel. Welcome, sir.
Thank you. Thank you for your introduction. Respected Chairman and respected Principal and respected Head of Department of Electronics and Communication Engineering, Konganadu College of Engineering, for providing me an opportunity to deliver the guest lecture on CMOS amplifiers for biomedical application. So the topic of today's session I'll just share my screen. Is my screen visible?
Yes, sir, visible, sir.
So as the FDP states that emerging trends and challenges in VLSI mixed signal processing for fourth industrial revolution. So on this topic, I have taken biomedical application for this topic. So how to design circuits for such applications. That's the motive behind this talk. To go upon to this topic, I just want to give some fundamental concepts on this topic, and then we'll go further for the high-end research topic. So in today's digital world, everybody is accessing the mobile phone, and in the mobile phone, if you see, there are lot of analog and RF components are available, whereas the digital components are very less compared to analog and RF components. That's why the first sentence I have given, like, if it can be done by digital, don't use analog. And analog IC design is complex. We should have a very strong background in physics, electronics, information and control theory, signal processing, and communications. And in analog circuit design, we can provide variety of state-of-art solution. When I say variety of art solutions, I just want to give a fair comparison with respect to analog and digital domain. So in VLSI, we used to say power consumption P is equal to CV square F. This is the power consumption. This V is nothing but the supply voltage, and F is the switching frequency, and C is the capacitance that is associated in the circuit. Okay, so, and in digital circuits, if you take AND gate, it is predefined by the truth table. So A, B, Y, if you take, so 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1. So it is predefined. So we can't change the properties of this AND gate, operation of this AND gate. Whereas the power consumption, delay, power, delay, and area. So all these three parameters can be optimized if you go in transistor level design. So in transistor level design, optimization can be done. So only three performance metrics are used in digital circuits to evaluate the digital system design. Whereas in analog, each and every block has got its own performance metrics, and it depends on the application in which the particular building block is going to be associated. So my area of research expertise is on design of low noise preamplifier for biomedical applications. We can provide n number of solutions. We know the biomedical signal ranges from few hertz to few kilohertz. Okay, from few hertz to some 10 kilohertz. That is the frequency range of biomedical signal. and this is a signal amplitude. Okay, signal amplitude. So the signal amplitude may be few microvolts to few millivolts. Okay, say some 5 microvolt to some 5 millivolt, something like that. The range of the signal level, the biophysiological signal level. And in biophysiological signals, the predominant factors signals are ECG, EMG, EEG, okay, electrocardiography, electromyelography, and electroencephalography. So all this signal will lie in the range of some hertz, 40 hertz to 60 hertz. That part will be of some physiological signals. Okay. And some low active potential, we use early action potential, something will be lying in 1 kilohertz to 2 kilohertz. This is in the range of hertz. Okay, so for these things, we need to identify an amplifier which is used to amplify this signal. Okay, so the performance metrics here, it comes like gain, the bandwidth, unity gain bandwidth, slew rate, noise, THD, okay, CMRR, common mode rejection ratio, PS, all these parameters you would be aware of it. But just I want to give a quick recap on it. That's it. So n number of performance metrics are associated to design an amplifier for biomedical applications alone. So once you targeted for biomedical application, this amplifier can't be used for some other application. Okay. Whereas AND gate, this in digital circuit, AND gate you can use in any digital system wherever the combinational circuits are used. The universal gate they have predefined like NAND, NOR, right? Similar to that, here we can't adopt. Okay, if a particular amplifier has been designed for some particular application for that only. Okay, so variety of state of art solution can be provided, and it is highly dependent on technology. So why we are saying that it is highly dependent on technology means, if you take the digital circuit, as technology, CMOS technology scales down, CMOS technology scales down, supply voltage decreases. Supply voltage decreases. So when VDD is decreasing, it has got a direct impact on power. Power is going to get reduced. Okay. Whereas in analog, there is a parameter named GM or not. Okay, this we used to call it as intrinsic gain. Intrinsic gain. Okay, for if you have got a MOSFET, for this MOSFET, it provides a gain of GM or not inbuilt. Okay, intrinsic gain. This gets reduced. Okay, as technology scales down, as technology scales down, this factor reduced, GM or not gets reduced. On the other hand, if you look upon the DC gain expression, DC gain expression, that which is given by the notation AV, is approximately equal to GM R naught. Okay, so we need high gain amplifier means we want this GM R naught to be high. For high gain amplifiers, for high gain amplifiers, GM or not should be high. So how we can increase this thing? That's what we are going to see in today's topic. How we can achieve a high gain amplifier and high speed amplifiers. Okay, so this if you want to increase this thing, power consumption is going to increase. We will talk in the slide, through the slide. Power consumption is going to increase. So as technology scales down, we won't say that low voltage is not low power for analog. In digital, low voltage is low power, whereas low voltage is not low power for analog. Will be burning more power. So it depends on if you are going to design in 180 nanometer technology and you are achieving a gain of 40 dB. Okay, if you are going to realize the same topology in 90 nanometer and you need to achieve 40 dB, means power consumption is going to increase. Okay, it will not be at the same power. Fine. So with this thing, this very high dependent, and we should have a good uh, background on modeling skills. Okay, how the MOSFETs can be modeled in various frequency of operation, and we require a complex EDA tools, electronic design automation tools. So these EDA tools we are in the industry, they are using predominantly Cadence, Synopsys, and mental graphics. There are so many EDA tools, electron design automation, EDA tools. So in this Cadence, Synopsys, and Mentor, these are very highly used in industry to design analog circuits. Okay, and there are Tanner and Arcade, P-Spice. Okay, there are so many spice tools, LT Spice, but in industry these are predominant. Okay, so we can't live without analog circuits in this digital world. That's why it's mentioned still necessary. So I have taken this part of this slide from the reference by Professor Francis Serra-Garelles, Department of Microelectronic Systems and Electronics, University Autónoma de Barcelona. Okay, so and the second thought, if you are going to use MOSFETs for digital system design, how the MOSFET will be visualized. It will be visualized as a switch, whereas in analog, the same MOSFET will be visualized as a switch, current source, capacitor, resistance, diodes. The visualization of a MOSFET in analog domain is more compared to the digital circuits using MOSFETs in digital domain is just going to be in triode region. Okay, so this is the visualization itself is having multiple elements in analog domain. So as the topic of today's discussion is going to be on CMOS, I'm going to present you the IV characteristics of the MOSFET. So we have got two IV characteristics. One is ID versus VDS for various values of VGS, and ID versus VGS. These are all the two characteristics, and based on the constraint, the device will be operated in triode region and saturation region, and we have got explicit equations to represent the drain current in each region of operation. So if you observe this equation, when your VDS is less than or equal to VD sat. That VD sat is nothing but VGS minus VTH. Okay, so we know the MOSFET is operated in 3 regions of operation: cutoff, triode, and saturation region. So the condition is ID is equal to mu n Cox W by L VGS minus VTH VDS minus VDS squared by 2. This condition is VDS is less than VGS minus VTH and VGS is greater than or equal to VTH. This is for triode. Similarly, for saturation region, ID is equal to half mu n Cox W by L VGS minus VTH whole square. The condition is VDS is greater than or equal to VGS minus VTH and VGS is greater than or equal to VTH. This is for saturation region, and our MOSFET suffers due to second order effects, namely body effect and channel length modulation effect. So body effect is when we stack transistor one above the other. When we stack transistors one above the other like this, you see so if you observe here, two transistors we are having M1, M2. So here the fourth terminal, bulk terminal, this also is going to be grounded. So that is VSB equal to 0. This is BES. This is for M2. Whereas for VSB of M2 is not equal to 0, due to which the threshold voltage is going to get changed. So these are all the device fundamentals. I'm not going to touch upon that one. Rather, just we should, as a circuit designer, we should be aware of it when we are going to stack transistors one above the other. The above transistor is going to suffer from body effect. Similarly, channel length modulation. So ideally speaking, if you see this in saturation region, the drain current is going to be like constant, whereas due to channel length modulation, you will have a slopy curve. That slopy curve is due to the channel length modulation effect. Okay, that is when your VGS is your gate voltage is going to keep on increasing, the electrons in the channel will move towards the gate, so the channel gets pinched off. That means the length of the channel is going to get reduced, due to which the current is going to be it's not going to be constant. There will be variation in the current in saturation region, and that is defined as 1 plus lambda VDS. So in the drain current due to channel length modulation, ID is equal to half mu n Cox W by L VGS minus VTH whole square into 1 plus lambda VDS. Okay, this is channel length modulation coefficient. Channel length modulation coefficient. Here this gamma is nothing but body effect coefficient.
Dear participants, due to some technical issue, our resource person get lifted. He will join soon. Kindly hold. So in the meanwhile, I will give some instruction to the participants. So at the end of each session, we will share a feedback form. So all the participants are requested to kindly fill that feedback and attendance form. While filling the feedback form, there is a one column called FDP ID. In that FDP ID, you want to choose your respective FDP ID. So that ID document is already sent through your WhatsApp and also through mail. So kindly check that after go and fill the form. Sir, sir, unmute your mic, sir.
I don't know, suddenly my system has got shut down. Sorry.
Okay, sir, no problem, sir.
Is, my screen is visible?
No, sir. Still now we didn't.
Yeah. Now?
Yes, sir. Now it is sharing, sir. Yes, sir. Visible, sir.
So we discussed about the effect of second order parameters on the MOS device uh, threshold voltage and in drain current. And now, since the topic of today's discussion is on CMOS amplifiers, so we should know the small signal model of MOS device. So in this diagram, if you see, this is the small signal model of the MOS device. So we can try to understand the MOS model in low frequency region first and then to the high frequency. So the MOS structure is given by this diagram: P substrate, N plus, N plus, this is gate, source, drain, and we have this bulk P plus. This is bulk terminal. Okay, so in low frequency operation, the MOS model is just given by a current source, okay, gate, this is drain, and this is source. So this is going to be GM times of VGS. GM times of VGS. And if second order effect is taken into account, or not, the slopey part is going to contribute a resistance. Okay, this is ID VDS. And we know this part is going to be saturation region, and it is going to provide you a slope. That resistance is given as R naught, and it is going to be 1 by lambda ID. So R naught we have taken. So this is in low frequency. Okay, this is silicon dioxide. SiO2. Okay, due to which only MOS has got high input impedance, because metal oxide, then semiconductor. Okay, this is p-type semiconductor, in which we are diffusing the n plus diffusion and p plus diffusion. So this is metal, this is oxide, and p-type. This is a semiconductor. So MOSFET is given as metal oxide semiconductor. Okay, and it has got high input impedance because it is going to act as an insulator. It doesn't conduct current. Okay, so it is going to be left open. Okay, and since it is going to be in saturation region, it is going to be, ideally speaking, it is going to be like a constant current source. That's why we are modeling it as a current source, which is GM times of VGS, and R naught is due to second order effect, channel length modulation. Okay, so this is in low frequency. Now the same visualization, now we shall try to see what in high frequency. In high frequency region, what will happen? See, this is p type and this is n plus, right? So this is going to be have one diode, right? Similarly, the drain diffusion is also, we are going to have other diode. Okay, PN junction. PN junction we are having at the, it's represent, it's a diode. Okay, so in CMOS process, always the P substrate is going to be like grounded. It is going to be like grounded. Okay, so drain will apply some positive potential, In so bulk is the lowest potential in the CMOS process while fabrication, and source, if it is grounded, fine. If not, some little bit of negative compared to the ground. So what I mean to say is these two diodes, we will call CSB, CDB. So these two diodes are going to be operated in reverse bias. So it introduces a depletion capacitance. In a PN junction under reverse bias, we got a capacitance depletion capacitance. Okay, this will also, we know the capacitance is Xc is equal to 1 by omega C. As omega increases, the reactance gets decreased. Okay, the capacitive reactance is going to get decreased, due to which sometime it becomes, for some frequency, it acts as a short circuit. So there won't be like source and bulk terminal in the device. Both will be like one and the same. Okay, fine. So this is going to be, we will get CSB and CDB. Similarly, oxide capacitance, COX. Okay, fine. And the overlap, if you see, due to fabrication process, between gate and source, some overlap. Okay, these two overlap contribute to CGS and CGD. Okay, CGS and CGD. Right. So these four capacitances are dominant in nature. So in high frequency operation of the MOS device, we use this capacitor CGD, CGS, CSB, and CDB. Is it clear? Right. So this is the high frequency model of the MOSFET. Next slide. So now we need to understand the differential amplifier. Any whatever the front end block of any system, okay, where analog signals are going to be processed, we require a differential amplifier. Why we go for differential amplifier? Why we go for a differential amplifier? So the first thing is, if you go with a single stage amplifier, this is the MOSFET. So in a single stage MOSFET, this is a common source amplifier. Okay, so V out, how we can write? V out is equal to VDD minus ID RD. This is the DC voltage. Similarly, V in is going to be the input signal. Okay, so the total instantaneous V in, like this, when you write, it is going to be DC plus AC. This is instantaneous. This is DC component, and this is going to be AC component. Okay, so we need to ensure the device is going to be operated in saturation region. Under this region only, your MOS is going to act as amplifier. Okay, MOS is going to act as an amplifier only in saturation region. Okay, so we need to ensure the MOSFET in saturation region, thereby a small, due to applying this small signal component, VGS, a small signal current is going to added over here. This is DC current. So this we can replace it with V out equal to VDD minus ID plus ID into RD. So for small signal operation, we used to ground this DC voltage source. For small signal operation, DC voltage should be short circuit or ground, and DC current source should be open circuit. This we know. This we framed based on the resistance of the IV slope. So IV. So if you see, whatever may be the voltage, my current is going to remain constant. That is DC current source. So if you take the slope I1, I2, V1, V2. So I for V1, what is the slope? Y by, so I1 minus I2 by V1 minus V2. Right? So I1 minus I2 is going to be 0. V1 minus V2, some voltage is going to be there. Okay, it is going to be 0. I by V is going to be 0. So when you change it like resistance, it should be 1 by I by V. This term is equal to 0. It becomes like infinite. That's why it is open circuit. That's why DC current is open circuit. Okay, so whereas for a DC current source, you can just draw like this: I, V, whatever may be the current that I am going to draw from the DC supply voltage VDD, my current, my voltage is going to remain constant. This is VDD. Okay, so again taking slope. So V1, V2, I1, I2. So V1 minus V2 by I1 minus I2. So 0 by I. So it's getting 0. So V by I is nothing but R. So resistance is 0. That's why it is short circuit. Okay, fine. So when you see for after biasing the transistor in saturation region and when you are applying a small signal, your Vout is going to be just small signal Vout is going to be just minus ID times of RD. This ID is nothing but minus GM times of VGS into RD. So your gain is nothing but minus GM RD. That is V out by V in. V out by V in. This V in is nothing but VGS. Okay. So as we discussed earlier, the gain expression is given as AV is equal to GM R naught. Right. So we need to draw the small signal model. So gate of M1, here you are going to apply V in. So this is going to be GM times of V in and second order parameters are not. This is drain from drain RD. Okay, this is going to be V out you are going to take and this is going to be source. Source is going to be grounded for common source amplifier. Fine, this is going to be V. So what is the gain we discussed? So the current GMV in is going to flow from the ground. Okay, so that's why we are writing V out is equal to minus GM times of V in RD parallel R naught if channel length modulation is taken into account. So we'll write minus GM RD parallel R naught. This is under low frequency. Now, if you take capacitances into effect, so we have got CGD, CGS, okay, and then CDB. So here bulk terminal, this is the circuit we have taken for our understanding. No? So this is bulk. Bulk is always should be ground potentials. Okay, so here we in, we out. So for small signal, we discussed VDD is going to be ground, RD. Okay, now we'll replace it with the MOSFET with the small. This is CGS, CSB, CGD, and CDB. Okay, the CSB, if you see, both the plates of the capacitor are connected to the same potential. That means no capacitance is going to get exist. This is not going to exist. Okay, only these three capacitances are going to exist. So we will take this one. This is going to be CDB. So now if you want to derive the gain equation, okay, the complexity of derivation becomes much difficult because we have got two nodes, right? We need to apply KVL, KCL to sort out V out by V in. Okay, there comes a theorem named Miller's theorem. Why we go for this analysis means we have derived the gain to be GMRD. So how long the gain is going to be maintained at GMRD till what frequency? This is AV, right? This is going to be magnitude. So GMRD. how long the gain is going to remain the same. Okay, till what frequency. So in order to understand that one only, we go for frequency response analysis. That is AC analysis, frequency response analysis. Okay, when you go with frequency response analysis, now we need to visualize the model, including the capacitive effects that exist in the device. That's why these capacitances and all we have included in the model. And now we are going to analyze the circuit for its frequency response behavior. Okay, fine. So if you see that the CGD, this impedance, this capacitance is connected between two nodes. Okay, so we can, in order to make our analysis to be simpler, we will adopt a theorem named Miller's theorem. Thereby, our analysis becomes very simple. What Miller's theorem states: if an impedance is connected between two nodes, it can be segregated into the individual nodes provided same current is going to be flown. Okay, so the current, what is the current that is going to flow? Vx minus Vy by Z. The same current, when it is going to be flown, we can segregate the impedance associated with X node and Y node. We'll name this as Z1 and we'll name this as Z2. This is Y node, Vy, right? Same current has to flow. So what is Z1 that is associated with that one? So we have to write, since same current is going to flow through that one, we will write Vx minus Vy by Z is equal to Vx by Z1. So Vx you can take as common, 1 minus Vy by Vx by Z equal to Vx by Z1. Vx gets cancelled. So Z1 we can write it as Z by 1 minus AV, where AV is nothing but output by input. This is Y and X. So this is nothing but AV. Okay, we can replace this one with Z1 as Z by 1 minus AV. Similarly for Vy also, we can write now when we take Vy minus Vx, we have to take. So we have to tell Vy minus Vx by Z equal to Vy by Z2. Okay, so Vy when you take common, 1 minus Vx by Vy by Z equal to Vy by Z2. Vy gets cancelled. So Z2 we can write as Z 1 minus Vx by Vy. This part is nothing but 1 by AV. Okay, fine. So Z2 equal to Z by 1 minus 1 by AV. Now in frequency response, frequency domain, this capacitance will be getting transformed like 1 by SC. The inductance is going to come as SL. Resistance remains the same, whatever may be the frequency. Inductors and capacitor are going to be frequency dependent component. So it gets transformed like 1 by SC. Now Z equal to, in the circuit if you see, that is capacitance CGD. So we have to write like 1 by SCGD into 1 minus 1 by AV. Similarly, here also it is going to be 1 by SCGD into 1 minus AV. Okay, so by segregating the capacitance, by segregating this capacitance that is associated with this node, now we can frame the analysis in a much simpler manner. So we will segregate this impedance. So how we will draw the same small signal model, right? The source resistance V in, right? And then the current source GM times of V in or not, and then RD, then CDB. Okay, CDB. We are not playing anything with CDB. So CGS also we are not, we can just connect CGS. Whereas this CGD alone, we are segregating with node 1 and 2. Okay, so we'll write that associated with node 1 as CGD to 1 minus AV. Here CGD into, I'll draw over here. This capacitance is going to be CGD into 1 minus 1 by AV. Okay, so when we do frequency response analysis for circuits, now well, we want to ensure till what frequency the gain is going to remain constant. Okay, what causes the gain to be roll off? What causes the gain to be roll off? The frequency dependent component will make our gain to roll off. How it starts rolling off? So we would have seen for frequency response analysis behavior in control system, a concept called transfer function. So which defines the behavior of the system for various frequency of operation. Or we can say Laplace transform of output variables to the Laplace transform of input variables with all initial conditions to be 0. So we can write H of S is equal to K into 1 plus S by omega Z1, 1 plus S by omega Z2 divided by 1 plus S by omega P1 to 1 plus S by omega P2. Okay, so if you observe the transfer function, there are poles and zeros available in the transfer function. So in circuit, each node, we need to remember each node contributes to pole, and feed forward path that connects input to output is going to contribute to a 0. Okay, so when you observe the circuit, we have associated with 2 nodes. So each node is going to contribute to a pole. So how we can determine the pole frequency? Pole frequency is given by omega p, is inversely proportional to the product of resistance and capacitance seen at the node. Okay, the pole frequency is given by the inverse of product of resistance and capacitance seen at the node. Okay, so when you observe here, this is node 1. What is the RS? Both CGS and CGD into 1 minus AV are in parallel, so we can have the summation of the capacitance. So omega, I'll write omega P1 is approximately equal to 1 by RS into CGS plus CGD into 1 minus AV. This is a pole frequency associated with node 1. Similarly, omega P2 1 by RD parallel R0 and CdV plus CGD into 1 minus AV. So it's going to be CdV plus CGD into 1 minus 1 minus AV. Okay, this is a pole frequency. So what I mean to say here is, as the frequency keeps on increasing, what happens? This capacitance will become short circuit. It becomes short circuit. Okay. So due to which the gain is going to be rolled off. So at omega P1, so we know if a pole is introduced, we will have minus 20 dB per decay, omega P1. And omega P2 somewhere here it's going to be there, means 40 dB. Okay, minus 40 dB per decay. And this is going to be termed as bandwidth. And the gain the frequency at which the gain drops to 1, this is termed as unity gain bandwidth. Okay, so from Bode plot we can infer what is the low frequency DC gain, what is the bandwidth, and what is the unity gain bandwidth of the amplifier. So this defines that till this frequency our amplifier is going to amplify the input signal. Okay, so based upon this thing, this is for single stage amplifier. Now for differential signal, when you see for differential signal, just a minute. So now here I would like to emphasize why we go for differential amplifier first thing. So now if VDD along with that some noise voltage, this is a noise voltage we are going to add. Okay, so if you have applied the input signal like this, the output signal is going to be like this, amplified. Whereas if noise is going to be embedded over here, then signal gets disturbed. It will not be like a smooth curve because VDD plus delta VN we will have. Okay, VDD plus delta. We want to remove this noisy component that distorting the output signal. So we go with a differential input signal. So when you go with the differential signal, that noisy component is going to get eliminated. Okay, so with this as a idea of the amplifier concepts, now we will go with the biomedical signal characteristics. As we discussed, the range of the biomedical signals frequency with respect to amplitude is shown in this figure. So here you can observe EEG signal is lying between some few hertz only, from millihertz to some hertz. Electrocardiogram, ECOG, local field potential, accent potential, electron myelography, all these signals are given over here. So we need an instrumentation amplifier. Already the signal levels itself is from few microvolts to few millivolts. The device itself will have some noise. So the Amplifier doesn't understand whether it is the signal that we have acquired or the device noise. That's why instrumentation amplifier come into existence. So we need to design an low noise instrumentation amplifier in order to process this biopotential signal. So the noise level should be less than 3 microvolt RMS. We should see to that the noise level is less than 3 microvolt RMS. And the power consumption also, the power consumption, 1 second, sir. So we need to design the amplifier which consumes low power. Why we go for low power condition means generally nowadays we are implanting some biomedical devices in our human body. Especially many of you would have aware about that device named pacemaker, which regulates our heart pulses. Pacemaker. Okay, is the battery lifetime. The pacemaker cost involved in the extension of battery lifetime. If it is going to be 2 year, then the device cost may be very less. If it is going to be some 10 years, the device cost may be very high, because we can't repeat the surgery again and again to a person who needs this device to be implanted in his body to regulate his heart pulses. That's why we need to frame design the amplifier in such a manner it consumes very low power so that the battery life can be extended. Okay, and when you are going to acquire the physiological signal, we use electrodes, ECG electrode. That will introduce an offset. That offset also we should be removing it. Okay, that offset will come around 10 to 100 millivolt. That also we should remove it. And the instrumentation amplifier should have high input impedance, high CMRR, common mode rejection ratio, power supply rejection ratio, and it should have high dynamic range. Okay, these are all the properties, characteristics of the instrumentation amplifier required for biomedical application. My research expertise is involved in this topic. Okay, so I'll be brief how we can design this low noise amplifier for this biomedical application. Nowadays, as the topic itself is suggest fourth industrial revolution. Now for our biomedical in biomedical application industry, lot of mixed signal processing is involved, for which the foremost front end block is going to be the instrumentation amplifier, without which we can't do anything, process the signal. Okay. So now, as we discuss how we are going to design this amplifier using MOS device, we are going to see. So impact of CMOS scaling on analog design. So as technology scales down, everybody knows that it leads to high level of integration. The speed of operation is also going to get increased. That is FT, the transit frequency of the MOS device increase. Okay, whereas considering in analog perspective, the signal to noise ratio is going to get decreased, because signal level, the supply voltage is getting decreased. So when the supply voltage is going to get decreased, signal to noise ratio is going to get decreased. And I said that intrinsic gain, GM or not, of devices are steadily reduced with gate length. GM or not is also getting reduced, due to which we need to burn more power. Okay, and this is the instrumentation amplifier block. Okay, the instrumentation amplifier block is shown in this figure, for which the transfer function is derived to be AV of S equal to C in by CF and 1 by 1 plus S CL C in by GM CF into SR of CF by 1 plus SR of CF. Okay, I am not going to derive this equation. Rather, I just want to see whether This topology, capacitively coupled instrumentation amplifier topology, satisfies the biomedical application requirement. So this topology should consist of a high pass filter. So that high pass filter is given by this feedback thing, CF, MH1 and MH2, that is RF. Okay, so SRF CF by 1 plus SRF CF. This is a high pass filter characteristic, which really helps us to remove the DC electrode offset. Okay, and this bandwidth Cin by CEF gives the gain, and if you are going to connect a load capacitor over here at V out, this capacitance and this GM, this triangle block is going to be the GM, transconductance block we used to say. So that will give you the bandwidth. Till what bandwidth the an instrumentation amplifier is going to amplify the signal. So this capacitively coupled instrumentation amplifier, it has got intrinsic inbuilt high pass filter characteristic itself. Okay, so this one, how we are going to design. That I will come. So this is the GM block. Okay, this is nothing but OTA, operational transconductance amplifier. Okay, so this one we need to design. So in MOS device, we have got three types of basic amplifier. One is common source, common gate, and common drain. Okay, based on this basic configurations, high gain amplifiers are designed. It can be CS cascade amplifier. We used to call this as cascade amplifiers. If CG is connected, this is going to be like cascade amplifier. Okay, so high gain amplifiers can be built using these basic amplifiers. Okay, so in designing high gain amplifier, high speed amplifiers for this application, generally we go with cascade amplifier. Okay, so cascade amplifier, in cascade amplifier we have got two types, telescopic and folded cascade. There are two types of amplifier in cascade configuration. So this is the configuration. V in, this is VB, this is CS configuration, this is CG configuration, RD, VDD. Okay, here what happens is this is common source amplifier. This current, okay, GM times of V in current is going to flow. This is bias. Gate is grounded for small signal. Okay, this is common gate amplifier. Common source means source will be grounded for small signal. Common gate means gate terminal will be grounded for small signal. This is DC potential. In small signal, DC potential will be grounded over here. Okay, so this is the common gate amplifier. So and one more amplifier is called as folded cascode. This is telescopic cascode and folded cascode again. Sorry. Just so this is CS and this is CG. See here, if you observe, B out, two transistors are stacked one above the other, right? So we have two overdrive voltages, V overdrive 2, V overdrive 1. So V out is equal to VDD minus 2V overdrive. Voltage headroom problem is going to occur. So to overcome that one only, we go with folded cascode. We go with folded cascode type. Here, if you see in the V out, okay, from VDD, this is going to be like open circuit for small signal. Okay, fine. So from V out only 1 over drive voltage. Okay, fine. So we are increasing the output swing in the folded cascode. Okay, this is whereas this is an NMOS device, whereas here it is PMOS device. In folding node, when you go with folding node, it becomes like PMOS device. So based upon this thing, there are two things we need to. One is telescopic cascode in differential configuration and folded cascode in differential configuration. Now we need to analyze the small signal voltage gain. So the small signal voltage gain is given as GM into R out. So we'll go with one understanding. So how the small signal gain can be derived. Okay. So AV is equal to approximately equal to GM into R out. So the lemma is to find GM. To find GM, short circuit the output node, apply test signal at input. Okay, short circuiting the output node, we'll go with half circuit. In differential amplifier, we'll see that due to symmetricity, we'll go with half circuit. So it becomes like here we, so M1, M3, M5, M7, VDD in half circuit. Okay, VB, and this is V out. So for small signal, we will ground this one, right? We will be grounding this one. DC voltage, VB3, VB1, all these things will be grounded. To find GM, what we need to short the output and apply a input signal. Okay, we need to. So the circuit gets simplified like this. So I out. This is going to be M3 and M1. What is I out? Same current only is going to flow over. So I out equal to GM times of V in, GM1 times, because we are applying input to the M1 transistor. So GM1 times of V in. So I out by V in GM is nothing but GM1. Okay, this is the GM. Similarly, to find R out, we need to find R out. So everything will be ground for small signal. Constant DC potential. So M1, M3, M5, M7. This is V out. So to find R out, short circuit the input signal and apply test signal at output. Okay, so I am going to apply a test signal Vx. Okay, Ix is the current. Fine. I am shorting the input to M1 transistor only. We will be supplying the input. If you see, I am shorting this one. Okay, so now you can see that we are going. This is going to be the output. So we will write this as R up and R down. Okay, so we at this node, if you see, R out is going to be R up parallel R down. Okay, so both are like symmetrical. M3 M1 and M5 M1, two transistor. Only thing, the device are different, right? PMOS and NMOS. So now we will take the lower bottom M3 and M1. We are going to see what is the impedance that is going to be seen from this output node, right? Vx, Vx. We need to calculate Vx by Ix. That is R down. Okay, how we are going to do? So now we can replace, try to derive the expression with respect to small signal. Okay, M3. Okay. M1. Vx, Ix. So M1, if you see here VGS is 0. VGS is 0. Gate, source, both are short circuit, right? So we can just replace the small signal with only R0 1. Okay. If you see here, we will be drawing the small signal to be GM times of VGS, gate, source. Both are grounded. Okay, that means this VGS is going to be 0. Only in the equivalent circuit, due to channel length R0 will be available. Okay, and then for M3, we will try to replace it with GM2 times of VGS2 we will write. Okay, VGS2 and channel length modulation R0 2. This is gate 2. Drain 2 is 3. Gate 3. Drain 3. So I will write GM3 VGS3. Okay. And this is going to be source 3. Okay, this has been grounded over here. And to this we are drawing, we are connecting the input, or test signal. X and Ix is the current that is going to flow through this circuit. Okay, so now here if you observe VGS3, how we can write? We can write like VG3 minus VS3. VG3 is 0. This is 0. So it is going to be minus VS3. Okay, so to avoid this negation, we will try to modify the upward direction. The current flow, instead of this one, we'll go with one and we'll write GM3 VS3. Okay, if you change the direction of the current, this negation can be avoided. Okay, so now if you see at this node, if you apply the at this loop, okay, from this ground to this ground, loop 1, if you apply KVL, Vx is equal to Ix. Ix is the current that is entering, and GM3 Vs3 plus GM3 Vs3 into R02, that is the drop. And then again, when this is coming, GM3 will go. So Ix into R01 alone will be flowing through this. This is Ix. Okay. So Vs3 is nothing but Ix into R01 to R02 plus Ix into R01. So Vx by Ix, if you see, it is going to be R02 plus GM3. This should be R03. Okay, the notation I should not change. R03, R01 plus R01. So this is going to be your R out. Okay, that is the impedance is so approximately we will write as GM3 R03 R01. Okay, the upward side also, if you see M5 M7 to this part also, we can write R up equal to GM5 R05 R07. So cascode device, this M3 is cascode device. Okay, intrinsic gain of cascode device into the bottom device is going to be impedance. Okay, this is cascode device. Okay, and the impedance of the bottom device, that is R02. So by as lemma, we can understand R out is going to be R up parallel R down. Okay, that is going to be GM3 R03 R01 parallel with GM5 R05 R07. Okay, so total gain is equal to minus GM1 into GM3 R03 R01 7. So how long this gain is going to, magnitude of AV is going to remain the same. Then we need to do frequency response analysis. Okay, so this I have taken like folded cascode. This equation is for folded cascode, but I derived it for telescopic cascode. Anyway, the difference is going to be only this part, R03 parallel R01. Okay, we know each and every node is going to contribute to a pole, so we can write 1 by R out into CL, and omega P2 is equal to 1 by RP2 CP2. So I'll just do that one. So we'll analyze. Okay, this is the stacked transistors. Now we have taken CL as the load capacitance. Okay, so now how many nodes are there? Here one node, here. Okay, let's name this as node 1, 2, and 3. So node 1 omega P1 equal to 1 by R out into CL, resistance and capacitance seen at that node. Okay, once this particular frequency has reached, once this particular XCL is 1 by omega CL. Okay, this will be grounded. Okay, this capacitance short circuit when omega P1 is reached. So this will become ground. When once if it is become ground, M3, this also is ground. So gate, drain. So when gate and drain are shorted, this is a very important concept. This is called as diode connected device. Diode connected device. The impedance is given as 1 by GM. Okay, so now it will be like 1 by GM, then M1 device will be there. Okay, this is the second node. So it is going to be omega P2 is going to be 1 by GM2 into the capacitance associated with second node. Okay, so it is going to be GM2 by C2. Okay, so this is how the pole frequency response we need. So in the same manner, here also we are doing omega P2. Okay, and AV is equal to unity gain bandwidth is nothing but gain into F3 dB. So that is given as AV into F3 dB. AV is what? Minus GM1 into GM3 R03 R01 parallel GM5 R05 R07. Okay, and omega 3 dB is nothing but 1 by R out into CL. That is nothing but R out is again GM3 R03 R01 parallel GM5 R05 R07 into CL. Okay, so unity gain bandwidth is nothing but GM AV into omega 3 dB. So if you substitute here, you find this and this will get cancelled. So you will have GM1 by CL. Okay, if you want to have high unity gain bandwidth, GM1 should be very high. Then you will have, or load capacitance should be very less. Either the way you can fix. Okay, and since it is a biomedical application amplifier, we want the noise part should be very less. So I'll touch upon the noise contribution of a device. Generally, for the MOS device, the noise characteristics is shown in this diagram. Okay, so at low frequency, the noise is termed as flicker noise, and at high frequency, it is termed as thermal noise. The frequency at which the flicker noise and thermal noise is going to meet at a point, it is termed as corner frequency. The frequency at which flicker noise, this red color, and thermal noise is going to, it is termed as corner frequency. Okay, and the expressions are given as 4kT gamma by GM for thermal noise for the MOS device, and for flicker noise it is given as K by WL Cox into 1 by F. This is the you should remember this part. So when you see the thermal noise contribution, if GM is very high, the thermal noise can be reduced. The thermal noise can be reduced. So there comes this part. I will just skip because I have given the explanation of the thermal noise voltage and the flicker noise voltage, how it is calculated, those things. Okay, so from the thermal noise, what we have inferred is if GM is increased, If GM is increased, your noise is going to get decreased. Okay, that's what we have observed. So how we can improve the GM? So in literatures, there are a lot of topologies. Okay, I'll just go with the topology so that you can understand. So this is the folded cascade basic topology. Okay, we need to increase the GM. We need to increase the GM of the OTA. So how we can improve in the sense compared to the conventional topology? Here they are splitting the transistors M1 and M2 into two, M1A, M1B. Similarly, M2S, M2A, and M2B. Okay, by splitting the input transistors M1 and M2 in this fashion, and M3 and M4 as M3A, M3B, M4 and M4B, we can increase the gain. I'll just show the final equation, the importance. Okay, see, in depth we can't discuss now, just the importance. The theme of this topic is how we are going to design a low noise amplifier for processing the biomedical signal. So to design a biomedical amplifier, the GM should be very high so that the noise can be minimized. So to determine the GM, all those things, the fundamental equations I have just shown over here to find GM for topology, how we need to determine. Okay, so with that as an understanding, I am going for this part. Are you able to understand what I try to convey? Can you respond to me? Shall I proceed?
Yes, sir, you can proceed, sir.
So if you see here, when we modify the topology, the GM is enhanced by a factor of K plus 1. Okay, K plus 1. When for the same power consumption, we are not burning more power. For the same power consumption, by modifying this topology from the conventional one to the modified one, which is termed as recycling folded cascade OTA, we were able to achieve a very high GM, that is increased by a factor of K plus 1. Thereby, all the analysis is going to be, if this one is going to be improved, the noise is going to get reduced. Okay, these are all available in the literature. In my PPT, maybe I have shared with your coordinator. You can also collect it from him. Similarly, further to improve the GM, again in literature, they have renamed it as improved recycling folded cascade OTA. What here they have done with respect to this topology, this M11 and M3B, again they split into two, M11A, M11B, and the M3B and M3C. Similarly, M12A, M12B, and M4A, 4B, and 4C. So again, they have split. You can see here. Okay. Again, they have split. Thereby, the GM is further improved. K by A plus 1. If A is 0.5, it is going to become like 2K plus 1. So the GM is going to be improved by a factor of 2K plus 1. Thereby, the noise is going to get reduced. Okay. So as a circuit designer, we should see to that how we can minimize the noise that is contributed by the device utilized for realizing the amplifier. Okay, right. So this is what, again, the same frequency response analysis, all those things are going to be the same. Now, with still for further reducing the noise that is available in recycling folded cascode and the improved recycling folded cascode. They come up with a solution, whichever the transistor that doesn't contribute to the GM, for those transistor, we can go with source degeneration. Maybe in BJT, we would have called emitter degeneration resistance. Here also in MOSFET, it is called as source degeneration resistance. So what it does is, if the degeneration resistors are used over here, the noise contribution that is going to exist by M3 and M4 can be further reduced. The noise contribution can be reduced further due to M3 and M4, because M3 and M4 draws more current. Okay, draws more current. So if current is more, the GM is going to be more. To reduce that GM, M3 and 4, the current noise representation in thermal noise is reduced by a factor of by the source degeneration resistance. Okay, and in the scaling terms are used. And then there is one more topology that has been given in the literature, named as folded cascode current scaling. So it is nothing but the recycling folded cascode. If you observe the diagram, recycling folded cascode and this thing, only the source degeneration resistance part they have added over there, thereby the noise is further reduced. Okay, and my part here in improved recycling. For improved recycling folded cascode, I have adopted the source degeneration resistance so that the noise is further reduced. Okay, the noise is further reduced, and then we were able to compare it with the literatures. For the same power consumption of 0.18 micrometer process, 1.5 microwatt of power. When you compare with the gain is going to be 40.17 dB, bandwidth 0.008 to 1.68 kilohertz. The load capacitor what I have used is 10. We should design an amplifier which is less than 3 microvolt RMS. So we were able to achieve the input referred noise to be 2.99 microvolt RMS. And the factor NEF, noise efficiency factor, how much the noise you have reduced. This is one figure of merit, because as we discussed in the first slide, various state of art solution, and it is highly dependent on technology. Okay, so this process 1.5 micrometer process, I am going to compare it with 0.18 micrometer process, means how I can say that my design is far better than the existing literature work, means noise efficiency factor. This is like a figure of merit. So this should be very less. Okay, this should be very less. So the noise efficiency factor is given like the input referred noise voltage square root of 2I total by pi into UT thermal voltage 4 kT into bandwidth. Okay, this is the formula used for calculating the noise efficiency factor. So due to which the proposed OTA by me has achieved a very low noise efficiency factor. It indicates that the noise is very, very less. It is more suitable for biomedical application. And in terms of power efficient factor, power efficient, so power also we have targeted, it should be very less. So this thing is also is very less. And THD at 1%, it defines total harmonic distortion. So for what range of your input signal our amplifier is going to be in linear condition. That one to evaluate is total harmonic distortion. I have able to achieve 5.9 millivolt because generally biomedical signals, it ranges from few microvolts to few millivolts. So up to 5.9 millivolt peak to peak. This is highly sufficient. Even though it is very less, we can have a trade-off between noise efficiency, power efficiency factor, and this is also fine. Okay, and CMRR, common mode rejection ratio. This also I'm achieving greater than 70 dB. Okay, fine. So these are all the performance metrics used for analyzing the designed amplifier, whether it is suitable for biomedical applications or not. Okay, so the literatures, I have shown it in the references, so you can just see, go through this thing. Now, recently also we have designed, compared to this thing, and just show our paper. Just show my paper, one more paper. So this has been recently published last year in this Springer journal. So here, if you see the GM block, again there is one amplifier named double recycling folded cascade amplifier. This is existing in the literature. So we incorporated source degeneration resistance to this amplifier. We incorporated the source degeneration, and we tried to figure it out whether the design amplifier can be suited for biomedical application. So the noise analysis, all those things we have done the GM, and we found that the noise analysis, the noise is further even though when compared to my earlier work, the input referred noise is 3.27, whereas the bandwidth, because this is I have mentioned like variety of state of art solution. No, the bandwidth what we have taken here is 5.69, okay, kilohertz, 69 hertz to 5.45 kilohertz. This is hertz. Okay, this is hertz, and this is going to be kilohertz. There is a, this K is here, 5.45 K. My earlier design was 8 millihertz to 1.68 kilohertz. So we were able to increase the bandwidth. So due to which some additional 0.27 microvolt RMS has been added as noise. But since the bandwidth is getting increased, the noise efficiency factor is getting decreased, because NEF, in NEF you see bandwidth. If I'm going to increase the bandwidth, the NEF is going to get decreased for the same. Okay, so here and here at the output side, so output 1.2 volt peak to peak, the THT has been measured either at the input side or at the output side. We can measure the total harmonic distortion. Okay, this is one paper, and this is going to be like layout. Okay, layout of the amplifier, and this file only we will be going for fabrication. If you are going to fabricate your amplifier design, so we need to send the layout file or GDS, graphical database stream file. So when we go for fabrication, we need to do the layout and then we need to send the GDS file. Okay, so to carry out the design process, we have used GM-ID methodology. There is a method called GM by ID. Based on this GM by ID methodology, we can speed up our design work. Okay, we instead of going like a trial and error, we can go with the GM by the methodology and then we can figure it out. And while we are reporting the results, no, we should ensure that what are all the transistors dominant transistor that are dominant towards noise contribution. So how many by performing noise analysis in cadence, you will get all this information. Okay, so these are all the things that we should know when we go with starting our design for what application we are going to target and what is the block we are going to use, and we should compare it with the literatures. Okay, so with this thing, I am concluding my talk. Maybe now the time is 11:50. We will have some question answer session. If any doubt, you can ask me.
Dear participants, if you have any doubts or queries, you can ask now. You can either post your question in chat box or else unmute yourself and ask with our resource person.
Any question?
Hello, good morning, sir. I am audible.
Yeah, tell me, ma'am.
Yeah, sir, I want to know more about the GM by ID technology you have discussed in this paper.
Yeah. So here, first we need to choose our aspect ratio of the MOSFET device. So what we have to do is first for individual transistor, for NMOS transistor, for in which technology you are going to design your amplifier, we need to plot this graph GM by ID versus ID by W by L. This plot we need to uh, get it from the cadence tool by drawing the schematic of the MOS device, plot ID was VGS, ID was VDS, all those things. And we need to do some manipulation in the calculator used on it so that GM by ID was ID by W by L. This is the plot we should get it. So once this plot we are having, then it defines the region of operation. Okay, this in this thing 32, right? This is like weak inversion region. The GM by D plot will be like this. You will get. So this is called as weak inversion region. So this is termed as moderate inversion, and this is strong inversion. Okay. So now we have to choose in which region of operation we are going to bias the transistor. So in considering the noise contribution, flicker noise, it is in low frequency. It exists in low frequency. Okay, so this flicker noise on biomedical signals, it lies in low frequency region. So flicker noise will be dominating at that for the biomedical signals, right? So we need to go for PMOS device to in order to have low flicker noise. First, we need to select the device based on the noise contribution of the device, right? So PMOS device, if you observe the flicker PMOS device, the flicker noise equation. Flicker noise equation, if you see WL, right? WL, this is so device area. If you are going to increase your device area, the flicker noise is going to get decreased, right? In a PMOS device, the charge carriers are going to be holes. We know that the mobility of holes is lesser than mobility of holes is lesser than mobility of electron, right? So if you observe the drain current equation, ID is equal to half mu n Cox W by L VGS minus VTH whole square. Mobility of this is electron NMOS device. If you are going with mu P, the current is going to become minimum. But for same current, if you want to design it with PMOS device, that can be compensated with W. That can be. So the device area will be more for the PMOS device for the current you are targeting. Thereby, the flicker noise can be reduced. The flicker noise can be reduced. And GM will be more in weak inversion region. These are all some fundamental concepts, eta VT, ID by eta VT. So GM can also be enhanced. If you are going to bias the transistor in this region for this value, okay, in weak inversion region, your GM is going to be more, thereby the thermal noise contribution can also be reduced. Okay, so we have to fix the region of operation. Thereby, once suppose 25 you have chosen, so you need to draw and you need to extrapolate. And what is the current you are? So you can write GM by ID is equal to ID by W by L. So GM by ID, if you choose as 25 and drain here the current, what is the current we are going to, the drain current in your design we are going to use, you can choose that one, so that W by L you can get it. So always we will have L equal to 1 micrometer to depending upon the W by L aspect ratio. If you increase your length, the drain current can be minimum, so that power consumption also can be reduced. Okay, so based upon this thing only, for different transistors, we need to fix the region of operation. Thereby, I'll show you in the table. So we need weak inversion or subthreshold region. Okay, subthreshold region. Because my application is on biomedical application, I need a very low noise amplifier and low power also. So GM at subthreshold region is going to be very high. So I am fixing the transistors to be in subthreshold region. Okay, and M11 and M12, this doesn't contribute to the noise. Some gain we should have. So we are fixing it like moderate inversion. Is it clear, ma'am? By fixing the region of operation only, we can choose the W by L.
Yes, sir. So thank you, sir.
So I request maybe this textbook will give you a good idea. Paul G.A. Jespers, the GM by D methodology, a sizing tool for low voltage analog CMOS circuits. How to get this plot in cadence.
Okay, sir.
This one you can get it from that textbook, ma'am.
Okay, sir. And
So
sir,
yes.
which reason is best if we design an amplifier for low process technology?
Subthreshold region, ma'am.
Sub-threshold reason.
Yes.
Okay, sir. Okay, sir. Can we design some amplifier which can work in moderate region? Is
Yes,
it possible?
moderate inversion, the equations analyzed in moderate inversions are not, it is like an empirical formula. So always we used to say that subthreshold region and strong inversion region, only maximum of the transistors should be operated at, what do you call, for some transistors alone, we will fix it in moderate inversion region. Usually we prefer like subthreshold and strong inversion.
Okay, sir. Thank you, sir. Thank
Yes.
you. Very nice
Yeah.
explanation, sir.
Thank you, sir.
Yes.
Sir, I think there is no more question from participant side, sir.
Okay. So
Let me wind up the session, sir.
yes. So thank you for. I would like to thank Professor Dharmalingam for providing him an opportunity to deliver this talk at this pandemic situation. Thanks a lot.
Thank you, sir. When educating the minds of our youth, we must not forget to educate their heart. In this way, I would like to thank our today's resource person, Dr. S. Kumaravel, Associate Professor, Department of Micro and Nano Electronics, School of Electronics Engineering, VIT University, Vellore, for providing a wonderful session on the topic of CMOS amplifier for biomedical applications. Thank you so much, sir.
Thank you. Can I leave?
Yes, sir, you can leave, sir. Thank you, sir. Dear participants, the day one, session one attendance and feedback link is posted in chat box. It will be open up to 30 minutes only. So kindly fill it soon. While filling the feedback form, please select your respective FTP ID. That FTP ID is separate for each and every participant. So kindly choose your FTP ID. And that FTP word for PDF is sent through the chat box. Kindly see that. Dear participants, the day one session one attendance and the feedback link is posted in chat box. Kindly fill it soon. While filling the feedback form, kindly select your FTP ID. The attendance only marked based on your FTP ID. So that a FTP ID PDF file is attached in the chat box. Kindly see that. Thank you all.
அதை அதை ரெண்டு சைடு வர ஒரு நாள் ஹஸ்பண்ட் இல்லைன்னா ஒய்ஃபுக்கு தெரியும்.
Sir, good afternoon, sir. Rajesh, sir.
Good afternoon. Am I audible?
Thank you, sir. Yes, audible, sir.
Yeah.
Okay.
So
So,
can you
start the
start?
session, sir?
Yes, sure.
Okay, sir.
Good afternoon to all gathered here. It's my immense pleasure to welcome our today's resource person, Dr. Rajesh Mehra, Professor, Head, Department of IT, NITT Chandigarh. Welcome you, sir.
Thank you.
The pain you feel today can be the strength you feel tomorrow. Before going to session, let me see the short intro about our resource person. He completed his BTech in Department of Electronics and Communication Engineering from REC Jalandhar and ME in Department of Electronics and Communication Engineering from Punjab University. And he got a doctoral degree in ECE domain from a Punjab University. His research areas are VLSI design, digital signal processing, FPGA and software-defined radios, multi-rate and adaptive systems, PLC, SCADA, photovoltaic cells and LEDs, and so on. He published more than 50 journals and he published more than 25 research papers in various national and international conferences. His professional affiliation in a lifetime members of ISTE and member of IEEE. He written a more than 30 theses in ME, MW, and PhD and got an award for the thesis. In this way, I would like to hand over the session to our today's resource person, Dr. Rajesh Mehra. Please, sir.
Thank you. Thank you, Professor, for nice introduction. My screen is visible to all.
Yes, sir. Visible, sir.
Okay, PPT is visible?
Yes, sir.
Right. So, good afternoon to all, and I welcome you in this session on VLSI design flow. As the professor said, I am Dr. Rajesh Mehra. I am head of Curriculum Development Department in National Institute of Technical Teachers Training and Research. So in this session, we are going to discuss various design flow for VLSI. And we will just go ahead with some softwares, how to use them, and what will be the flow for using those softwares. So outline of this whole session, it will include, first of all, it will be overview. Then design flow, we are going to discuss. Then we will discuss front-end design flow and back-end design flow. What is front-end design and what is back-end design in VLSI. Finally, we are going to conclude and then references. So first of all, overview. Actually, first of all, we should be very clear about the domains. Normally, there are 3 domains in VLSI which are used for IC design. And these 3 domains are behavioral domain, structural domain, and physical domain, right? So behavioral domain here means when we write code or when you write program for your circuit, you can say. So in behavioral domain, we write our program, and that program can be in any language. HDLs can be used. HDL here stands for hardware descriptive language. And under HDL, again, there are 2 basically options. Either you can go for VHDL or you can go for Verilog. Right, these 2 languages can be used for your behavioral domain. And in this behavioral domain, you write some instructions, then you go for subroutines, and then you define your system, and you make your system application specific, right? So basically writing a code for your behavior, what kind of behavior you want from your system, it comes under behavior domain. Next is basically structural domain. Structural domain is nothing but it is in the form of, you can say, it is graphical representation. Sometimes like we say that behavioral domain is programming and structural domain is graphical representation. And here we use straight away symbols. Symbols, we can use transistors straight away to design our circuit. We can use gates, we can use adders, registers, or straight away we can use processors in our design to make further our IC. So these 2 domains are there, programming kind of, or you can say textural, because we are writing program in case of behavioral domain. So that is your textural domain. We write program in text form, and structural domain is in the form of symbols. Either you can use transistors or you can use registers or gates. And another domain is your physical domain. In this physical domain, basically, we work on straight away on, you can say, silicon area. We create transistors here in this domain. Transistors in the form, we create PN, junctions for them, gate, right? So basically, we work on silicon and we create transistors, and then from those transistors, we create cells, then modules, and then complete chip. So if we talk about front end and back end VLSI design, when we talk about front end VLSI design, then mostly we work on behavioral domain and structural domain. These two domains are very important. And when we talk about this backend VLSI design, then all these three domains are active. Either we can start with the physical domain, or we can start with our structural domain or behavioral domain. All these three domains are active. You can work in any one of these domains. Yes, depending upon the software, what kind of software you have, only then you can choose the domain. So three domains, in which domain you want to work, that will be decided by the input you have, what kind of input you have, whether you have input in the form of text code, you have information in the form of symbols, you have information in the form of physical structure. Depending upon, you have to decide the domain. Then depending upon that, you have to check the software. You should have that particular software with you also, because for front end design we need some other software, and for back end design you need some other software. Sometimes we start from front end and we end up with the back end. Some vendors, they provide complete solutions. Some vendors, they are working on only front end design. Some vendors, they are providing only solution for back end design. So all these things should be very clear to you before starting any design in VLSI. Now, then, first of all, what are the important parameters for VLSI? Whenever we are going to start our circuit, or let me tell you, this is really very hot area these days for research. If you are going for research in the area of VLSI design, normally we work on following parameters. First is performance. Performance is very important parameter of VLSI design. Under performance, there are various parameters like speed. Whenever we design a circuit, we try to keep our speed high in order to compete with other, you can say, products in the market. Power is very important factor when we talk about portable devices like your mobile phones, your laptops. In that case, power is very important. So power consumption of your circuit should be less, so that you can say your battery backup will work for longer time. Functionality here means whatever basically function you are expecting, or whatever logic is there in your mind, your circuit should work according to that logic only. Only then we can say that yes, our circuit is working according to our need, and whatever we were wanting, it is functioning as per our requirement. Flexibility is basically, it is also very important parameter. Flexibility means modification. If you want some kind of modification in your circuit later on, then your circuit should be ready for those kind of modifications. And this important factor is more useful in case of front-end VLSI design, because front-end VLSI design, it is based on FPGAs. FPGA stands for Field Programmable Gate Arrays, and Field Programmable Gate Arrays basically they are reprogrammable, and you can modify them at any moment of time. Means later or future modifications are possible with the help of FPGAs. So size of your circuit, and size is basically going to decide the area of silicon or die area, and it is also related with cost. If you are going to consume less size, then cost of your product will be less. And third parameter is time to market parameter. Basically, whenever you are going to start any circuit, you should be able to complete it within a specified time limit, basically. So you have to develop the product in less time. Means whenever you are going to start some product, you should have some time limit in your mind, and you have to launch that product within that time period. If within that time period some other competitor, they are going to launch the same product maybe at low cost, then you are out of the market before the launch of your product. So time is very important parameter. We have to take care of time also. So these are some parameters in VLSI design, and whenever we go for any product design or for any kind of research, then we normally we work on these areas. Either we are going to enhance the speed, or we are going to reduce the power consumption. Flexibility, as I told you, it depends upon the front end design or back end design. And you have to basically, if you want to compete in the market, you should be basically, your product should be cheap as compared to others, so that you can survive in the market, and you should be able to launch your product well within the time. So these are some parameters, and we normally work on these parameters. So two possible VLSI design options are basically, first is your application specific integrated circuits, ASICs you can say. And ASICs is basically, it is chip design based on specific applications using backend design tools. So we can say that whenever we are working on ASICs, it means that we are working on backend tool, right? So some examples of backend design tools are Cadence. They are leader in this market. They are providing good solutions. Another similar leaders are Synopsys, Mentor Graphics, Microwind, Tanner. So these are some, you can say, vendors who are providing backend design tools, and you can use these tools for your ASIC design. And then second part, as I told you, is programmable integrated circuit. Programmable integrated circuit means these ICs are programmable. You can program these ICs number of times. These are reprogrammable. So modification is possible in case of programmable integrated circuits. And example of these is SPLDs. SPLD stand for simple programmable logic devices. CPLDs, complex programmable logic devices. And FPGAs, field programmable gate arrays, and these are basically programmed with the help of front-end design tools like Xilinx ISC. So this software is, it's, you can say, educational version is available on net. You can download this educational version and you can work on this software easily. So this is for front-end VLSI design. Now, just a brief idea about the design flow. There are major 5 steps in our complete design flow. We can say that. First is system specifications. You should have specifications. Whatever system or circuit you want to design, you should have complete specifications of that particular circuit, right? So these specifications either you can get from catalogs, or you can get from research publications in that particular area. And those specifications you can use, you can finalize those specifications, and then you can use those specifications for your code development, right? So this code development basically here, it can be your, you can say, MATLAB code development, it can be your VHDL code development, or it can be your Verilog code development. Any means platform can be there, but before developing your code, you should have the specifications. What is your requirement? And accordingly, you have to select the specifications. Then once your code is developed, as you know that whenever we develop our code in MATLAB, what is the next part? Next part is we have to simulate it. And after simulating our code, we check whether our developed code, it is working as per our requirement or not. If it is not working, then again we have to do some editing in our code so that it should work according to our requirement. Then again we simulate it. And when we talk about VHDL, in VHDL basically, again we write our code either in VHDL language or in Verilog language. Then um, then again we check its behavioral simulation. We check the behavior of your of our circuit, and we analyze it, whether it is working as per our requirement or not. Otherwise we have to make the editing again. Then once our simulation is done, it is working as per our requirement, then the next thing is now we have to synthesize. Synthesize here is nothing but synthesize means now here you are going to check how much resources are required to design that particular circuit, and what is the speed of our circuit. How much resources are required in terms of how many transistors, gates, or your modules, how many of them are required. You will get all those information in this synthesis part. And also it gives you the information about the speed of your circuit. And once we can say that resource requirement, once that resource requirement is there with you, then you can compare it with the existing results. You can check whether area consumption of your circuit is more or less as compared to others. Likewise, once speed is known to you about your circuit, then we can compare that speed with the existing speeds, and then we can check whether our design is working at higher speed or it is working at lower speed. So in this way, we can analyze, and then we can further make changes in our circuit in order to improve the results. Then the next step is, once your synthesis is done, now your resources are known to you, means these are the resources required by you. Then the next part is PAR, placement and routing, right? In placement and routing, what we do, we place the required resources, because now after synthesis you know the required resources, what are the resources required by your circuit. You basically now place those required resources either on silicon area in case of backend VLSI design, or you place those resources on prefabricated logic in case of front-end VLSI design. Once your resources are placed, right? Once your resources are placed, the next step is you route them. Means you are going to make the interconnection between different resources, different components on your circuit, and you complete your design. So your routing part, it should be 100% complete. Only then we can say that yes, our design is complete. So after placement and routing is decided, then we implement it, right? Then we implement it means we implement it on basically actual environment, and we test our circuit. We test our circuit in actual environment, and we verify the logic, whether it is working as per our requirement or not, means whether it is our logic is fulfilled or not. So these are the 5 major, you can say, steps in design flow, and these steps are true for both cases, whether we are working in you can say this one front-end VLSI design, or we are working in back-end VLSI design, right? So with this major idea about the different steps, now I'm going to give you examples of this one. First is system specifications, right? Here system specifications means I'm taking one example of filter design, and you can design filter either on FPGA, or you can design filter on you can design one ASIC for filter. So in case of filter design, you need these different specifications. Its cutoff frequency, what is the pass band frequency, what is the stop band frequency, then passband ripples, and what should be the order of the filter. All these things will be there with you, right? So by taking all these things, you are going to design that filter. Then your filter order is going to determine the performance in terms of area consumption and speed. So if filter order is more, let us say filter order is let us say 100, right? In that case, you will have 101 coefficients, and if you want to enhance the speed, then you need let me tell you one thing. For speed enhancement, we have different architectures, right? Different architectures, actually 3-4 major architectures are there. First one is your fully parallel architecture. Second is fully serial architecture. Third one is partially serial architecture. So these type of different architectures are there. So let us say I want to enhance the speed. Then I will go for what? I will go for fully parallel architecture. Fully parallel architecture means you will get your output just after one clock. Means on every clock you will get your output. So it means that speed is high. But for that, let us say, as I was telling you, let us say the filter order is 100, you need 100 coefficients, and 100 coefficients, to process those 100 coefficients, we need 100 multipliers, and multiplier is the costliest part of our circuit. So it means that I have to use 100 multipliers by using, but by using that 100 multipliers, I am going to use more area. It means that more area, more multiplier, it means that cost will be high. So we have to select our filter order very, means you can say precisely, because it is directly related with speed and area. So it means now 100 multiplier, it will be costly, but its speeds will be high. On the other hand, if we are going to make our product cost effective, in that case, we can go ahead with our fully serial architecture. In case of fully serial architecture, we are going to use only one multiplier, right? We are going to use one multiplier, and all those 100 coefficients will be processed by single multiplier. Then after how many clocks you are going to get your this one output? You will get your output after 100 clocks. So just see the difference between two: fully parallel architecture and fully serial architecture. So in case of fully parallel architecture, you are getting your output after 1 clock, and in case of fully serial, you are getting your output after 100 clocks. It means your this one fully parallel architecture is 100 times faster than your serial. But we have to now, if we have to optimize both your cost and speed, then we can opt for partially serial kind of architectures also. In that case, let us say we are going to use 25 multipliers instead of 100 multipliers. So when we use 25 multipliers, in that case, each and every multiplier is going to process 4 coefficients, right? So 4 coefficients by each multiplier. It means that in one first clock pulse, first 25 coefficients will be processed. After second clock, next 25 multipliers will be coefficients will be processed, and then third clock, next 25, and fourth clock, next 25. It means that you are going to get your output after 4 clocks. By reducing your multipliers 1/4, we are getting our speed fast as compared to serial architecture. So these are different options, and whenever we go for our design, we should be very clear whether we are going to enhance the speed, or we are going to reduce the cost, or we are going to optimize both speed and cost. Accordingly, we have to select the architecture, right? So just by keeping all these things in our mind, we can say that filter order must be kept minimum possible by meeting the required requirements, or we can say by meeting the required specifications, right? So once these system specifications are clear, along with other inputs, required inputs, we go for the next step. Next step is, as I told you, it is code development, right? So code development, basically, you can say that it may be MATLAB code or it can be HDL code. MATLAB code, normally we say that it is M code or HDL code. So we can design our filter and we can simulate it using desired specification in MATLAB. Then we can design its HDL, hardware descriptive language. Either we can write VHDL code or we can write Verilog code for simulated filter using suitable architectures. These architectures I have already explained to all of you. First one is fully serial, second one is fully parallel, and third one is partially serial. So that thing will be decided, and based on that, we are going to go for our VHDL coding or Verilog coding. So we have to select these architecture to meet the desired performance in terms of speed and area, as I already told you. So if we have to optimize, then we can both, then we can go for partially serial. But if we go for speed, then parallel architecture is best. If we are going for area, then serial architecture is best. It depends upon what? It depends basically on the applications. For which application basically we are going to use these architectures. For example, I can give one example where we can go for for parallel kind of designs. For parallel kind of designs, I can give you one example, like in medical imaging, right? Filters are very important. For example, when we go for MRI, all of you know that all these kind of tests are very, you can say, costly, and their machines are also too much costly. What is the reason behind that? Why those machines are so costly? Because in that case, you need accuracy and you need accurate results in a very fast way. Means in real time, whenever you are scanning human body, and simultaneously you are checking or analyzing on the screen. It means that you are getting output at the same time. When you are getting output at the same time, it means you need high speed. Or in medical imaging, because it is a matter of human life, we are basically dealing with human life. In that case, we can't take risk, right? We need accurate results because it is a matter of human life. So in that case, we never compromise with cost, right? So in that case, we go for parallel architectures. We are not bothered about the cost. We are bothered about the speed and accuracy of results. That is one example for parallel designs. Another example, I can give you one example for serial architecture. Serial architecture we can use where basically we are getting the signal. We are storing it in our hard disk, and then later on we can process it. Means there is no, you can say, no need of high speed. For example, sometimes you are downloading some images or videos, and then you are processing them at the later stage, right? So in that case, it can be processed anytime. So there is no problem. We can basically work with serial architecture. And partially serial, where we need speed, basically where we need optimized design, optimization in both speed and cost, right? So one example is your mobile phone, right? In mobile phone, basically when we are talking with each other, and in that case, yes, we are bothered about speed and also cost, because we are very much basically bothered about the you can say cost of the mobile. So in that case, let us say at some time speed is not working due to some reasons. If your call is dropped, we can again make a call. There is no problem, because no life is involved here. So in that case, we can make some compromise, but in medical side, we can't make any compromise. So in this way, basically, you have to select the application, for which application you are going to design your circuit. Accordingly, you are going to select the architecture of your complete design. Now, once your code is ready, then the next step is you have to now simulate it. You have to simulate your code, and design simulation verifies behavior of your developed logic for its functionality. So functionality is very important part. Whatever logic is there in your mind, and you are just designing your circuit based on that logic. And when your code is ready, you have to check the functionality of your circuit, whether it is working according to your logic or not. So you have to check the functionality in simulation. And I already explained what is synthesis. Synthesis basically it is used to compute the resources required for your circuit, what will be the speed, and also it is going to give you the information about the power consumption of your design. So basically, first point is related with area, second is with speed and power. And in VLSI, these three parameters are most important. And whenever you are going to encounter any research paper related to VLSI design, you will see that either those papers are working on speed, or they are working on area, or they are working on power. So these are very important parameters. Now the next step is placement and routing. Placement basically is used to place the developed logic on silicon area in case of ASIC or backend VLSI design. And we have to basically place the logic or resources on prefabricated resources, as I told you. And those prefabricated resources are, or prefabricated or existing resources, these are some examples are there. CLBs, here CLB stands for combinational logic blocks, or PLBs, programmable logic blocks, in case of PLDs and FPGAs. So if you are working on front-end VLSI design, you are going to use existing resources. In case of back-end VLSI design, you are going to use silicon area for placement of your resources. Then the next part is routing, and routing is basically it is used to find optimal path between placed resources, or you can say shortest path or optimal path between placed resources. So basically, efficient placement routing plays an important role to achieve what? Placement and routing, it plays very important role in all the three parameters, and it is related with your what? It is related with your speed, area, and power. So your proper PAR, it can enhance the speed, it can reduce the area consumption, and it can also consume the power consumption. So whenever you will see or search the net, you will see that placement, there are number of algorithms for placement, there are number of algorithms for routing also. And you can get papers related to these placement and routing algorithms. So here also, even in placement and routing, you can start your research. Then implementation, where you are going to implement your design after placement and routing. And it can be implemented on SPLD, CPLD, and FPGA when we are working on front-end design. And it can be implemented on ASIC when we are working on back-end VLSI design. So just keep these two things in your mind. In VLSI design, depending upon the, you can say, software with you, you have to select front-end design or back-end design. Now, first of all, I'm going to discuss what is front-end design. how to move ahead with front-end design and what are the different steps in front-end design, right? So first of all, in front-end design, basically there are 3 steps, and you can choose any one. Not 3 steps. There are 3 options. Sorry, there are 3 options, and you can select any one of these 3 options for your front-end design. You can go ahead with any option. First is your, let us say, HDL development. Second is core gen. Third one is DSP tools. These are very important. Actually, let me share my experience with all of you. Most of the time, we are afraid from hardware implementation of our circuits. We are very comfortable with what? We are very comfortable with software based solutions and simulations. And we try to get escape from hardware kind of things. But let me tell you, if design flow is clear to you, and options of different software are clear to you, you can easily go ahead with your hardware implementation. So there is no need to basically get away from the hardware implementation. The only thing, you should know the exposure of softwares, and what are the different steps and how to use those softwares. That thing is most important. So first is HDL development. Okay, HDL development flow is basically, in this case, you are going to write HDL code. Either you can write your code in VHDL, or you can write your code in Verilog, right? But in that case, you should have thorough knowledge of either VHDL or Verilog. Only then you can write HDL code. Likewise, in MATLAB also, you should be clear about M coding. You have to write M code of filter if you are comfortable with this, right? Now, here question is, if you are not comfortable with HDL design, what are the other options then? You don't know HDL coding, then what? I will tell you that thing also in coming slides. First, let us suppose that you are comfortable in HDL coding. Either you are comfortable with VHDL coding or Verilog coding, you are designing your own code. So you are designing your own code, that is part of your HDL design. Next is, now you are synthesizing it. Now synthesizing your code here, after HDL, basically, you are going to check its behavioral simulation, develop the code and simulate it. Then next is synthesize. Synthesize basically, again, here in this part, you will get the idea about the resources, right? What kind of resources are required to implement my circuit, and then the next part is your speed. What is the speed of your design? So once in synthesis, resources are decided, means these are the resources required for your circuit, then we go for its implementation. Its implementation, basically, it includes your PAR, placement, routing, and mapping. One more thing is there, that is mapping, right? So synthesis, here I'm telling you, you are basically going to check the required resources along with its net list. What are the resources required, and how these resources are connected with each other. And then we check its functional simulation. In implementation, as I told you, there are 3 things now. In implementation, translation, placement, or routing. These three you can say steps are performed in implementation, and it is used for timing simulation. Translation also, sometimes it is called as mapping, right? So just let me give you one example of translation. Let us say that after your synthesis part, it is decided that in your circuit 10 adders are required. So after synthesis, you came to know that 10 adders are required. And in your software, right? In your software, you have the option of 20 adders. 20 different kind of adders are available in the library of the software. And out of those 20 adders, you have to select one which is more optimal. Which is more optimal in terms of what? In terms of speed, in terms of cost, you have to select the one. So that part comes under basically design, synthesis, different algorithms are there for that. So under translation, out of those 20, you will select one. So basically now the required adder, those 10 adders will be mapped with the one selected out of 20. That is translation or mapping. You have to select suitable resources from the existing components present in the library. So once those suitable components are selected from the library, then you are going to place them. You are going to place them on the either existing resources, or you are going to place them on silicon. Once those are placed, then we make interconnection between them. We make interconnection between them, and we find out optimal path between them. Optimal path, you can say, that is the shortest. And again, I'm telling you, your placement and routing plays very important role in all those three parameters: speed, area, and power. So these three things are done in implementation. And when we when your circuit is placed and routed, then in case of front-end design, in case of front-end design, once your this routing is finalized, as I told you, front-end VLSI design means programming of your circuit. And programming of circuit, basically it is done with SRAMs. You have to make the connections of your nets with RAM. Let us say, or we call them as programmable interconnects in your FPGAs. So let us say there are 100 programmable interconnects, and when you route, when you place and route, then you came to know that out of 100, you have to program 30 programmable interconnects. So 30 programmable interconnects means, and each interconnect is related with one bit, one single bit, right? So if there are 100 programmable interconnects, it means that there are 100 bits, okay? And out of those 100 bits, you have to basically program 30 bits, and those corresponding 30 bits will become 1, and others will remain 0, right? So that is known as your bit file. Here you can see that. Generate bit file, bit stream. So bit stream, 100 bits, out of those 100 bits, 30 bits are 1 and others are 0. 30 bits are 1 means that root is connected. Now, when it is 0, that is open. Fine. So generate the bit stream, and in case of FPGA, you only download that bit stream. That bit stream will go from your PC to FPGA, those 100 bits. And those 100 bits are going to program the FPGA. Wherever 1 is there in that bit, that programmable, you can say link, that will be closed. And wherever it is 0, that will remain open. So once it is done, downloading is successful, then we can verify our circuit on hardware. We can check our circuit on actual hardware. This is the complete process of your HDL development flow. Next, I told you that we can have some options, like if you are not comfortable with code writing in VHDL or Verilog, then what? Even then we can go for our code development or not. What will be the option in that case? So in that case, you have one option in ISC environment, that is CoreGen. CoreGen basically it is used to generate your code. So you will have option of, here you can see that you will have different IP solutions. You can say these are IP cores, and wherever it is marked with green, those are those license, they require license fees, means these are not free. P are parameterized based, you have to enter the parameters for them where P is written, and S means project license available. S you can work on them, right? So you can say that if you want to generate code related to these things, here you can see that FIR filter is already available. MAC filter is available. So just what you want, what you need just parameters. You have to enter the parameters and you can generate the code. There is no need to basically worry in writing VHDL code. You can easily generate both VHDL or Verilog code with the help of this CoreGen. So these are some DSP related functions which are available in your CoreGen, and these are some paid versions. These are some parameterized version. Most of them are parameterized. You know the specifications only, then you can work on these functions. Then some math functions are there. You can see that, right? And then base functions, and then memory functions. So you can use these different functions, and you can generate code for them. Rest of the steps will remain same. Now your this part is over, synthesis is same, and then up to here it is rest is same. The remaining steps are same, similar to previous design flow. Only here what is the addition, you can say that you have the now ready-made code with you, and you are working on that particular code. So now with this diagram you will be more clear. First of all, what I am doing, I am writing the code. This is VHDL code, right? This code is basically developed, and once this code is developed, then it is simulated, and we have synthesized it. After synthesizing, netlist is generated. After netlist generation, we are performing what? Here you can see that I am writing map. There it was translation, translate. So both are same things, but either translate or map. We can map, then we have to place and route. Next step is generate bit stream. As I told you, there may be number of programmable interconnects, and those programmable interconnects are related with 1 bit, and 0 means that particular programmable interconnect is not programmed. 1 means programmed, means connected. This program is these are connected. This is open. So once this bit stream is generated, only this bit stream will be transferred to your this you can say FPGA, right? And then we can check you can say working of this you can say code, whatever code we have written. So here you can see that these are the inputs and this is the output. Here one switch is down, another one is up. You can see that. So basically one logic was developed, that is XOR gate. In case of XOR gate, you know that when any one of the input is 1, right? In that case, your output will be 1. So here you can see that this input is 0, this is 1. That is why this output is on. So it is working. So in this way, you can check your code on actual hardware. This is FPGA board, and you can check your output on this hardware board. So these two steps are there. If you are basically comfortable with the HDL language, then you can go ahead with HDL codes. If you are not comfortable with HDL language, then you can go ahead with your DSP tools, right? So and the next is our DSP tools. In DSP tool, basically, I can give you one example in this one. As I told you, we can design our filter in MATLAB, and then we can go to our ISC environment. So here you can see that this is your MATLAB environment and this is your ISC environment, and there is a gap between these two. What is that gap? Basically, this MATLAB provides us it provides us floating point numbers, right? Floating point numbers, and but our ISC environment, it takes fixed point numbers. It takes fixed point numbers. It means that it takes the input in terms of zeros and ones, right? So once your MATLAB code or filter is designed, that will be in the form of a floating point number. Now you have to convert that floating point into a fixed point, right? It means that you have to assign the bits with your inputs and outputs. Whether you want to use 16-bit for your input or you want to use 16-bit for your output. So those bits you have to assign, and then only then you can work in this ISC environment. So how this gap can be filled from floating to fixed point? In that case, we use these DSP tools, right? DSP tools are used for that purpose. Actually, two important tools are there in DSP. First is your system generator, and second is your Excel DSP. We can use system generator or we can use Excel DSP in our case, right? What is the purpose of system generator? Where we can use system generator? As I told you, there are I told you about the three domains. One was behavioral, another one was structural. Actually, this system generator, it works with structural domain. Structural domain means graphical domain or pictorial domain. As you know that in MATLAB, there are two methods of designing your system. One is MATLAB code, another one is Simulink, right? MATLAB code is your textural environment, and Simulink is your graphical environment, where we use what? We use blocks, block diagram to design our system. And in case of MATLAB, we use code, M code. So if you are working in Simulink, then we use this system generator. And this system generator, basically, it bridges the gap between your MATLAB and ISC environment. So this system generator is very important tool. As per my experience, most of us, we are more comfortable with what? With block diagrams. And we are less comfortable with the coding. But both, they have their own advantages and they have their own disadvantages. If I say M code or coding or textural language, advantage of textural language is it is easy to modify, right? And its disadvantage is it is difficult to understand. Means if someone has written some code, if other designer want to understand that particular code, in that case it will not be very easy. It will be difficult to understand that particular code because everyone's thinking is different. On the other hand, if we talk about graphical language is easy to understand. Block diagrams you can easily understand, but it is difficult to modify. So we can say that both these languages, they have their own drawbacks and advantages. So if you are working in system generator, then sorry, Simulink, then you have to use system generator. You can use this system generator. It is going to bridge the gap between your this MATLAB environment and ISC environment, and it is going to generate the code for you. Again, you don't have to worry about VHDL and Verilog code. This system generator is going to generate code for you. Example of this one is, here you can see that I'm using block diagrams, right? So you are not writing any code. This is in the form of block diagrams or graphical representation, and I am simulating it. This is one example of your Simulink and system generator, and they can be used, and you can easily generate your code with the help of this one, system generator, right? Next one is, as I told you, Excel DSP. Excel DSP is used when you are working in code designing, M code. When you are developing M code, in that case, that gap between your ISC environment and MATLAB is bridged with the help of Excel DSP. So if you are working in M code, then you have to use Excel DSP. It is going to convert your floating point into fixed point, and it is going to generate code for you again, right? Again, there is no worry about code generation. You will get automatic code with you. So in this way, you can easily design, you can say, complex systems, and whether you have the knowledge of HDL coding or not, you should know the softwares, what are the software available, and their steps, how to use them. So in Excel DSP, here you can see that in Excel DSP what we are doing. Here we have the code. We are writing one M code, and we are simulating this M code. Now this is floating point number. That floating point will be converted into fixed point by using Excel DSP. And after converting into in fixed point, this Excel DSP is going to generate HDL code for you. It is going to generate either VHDL or Verilog, and then you can take that HDL code and you can work on ISC environment. So in this way, basically, you can bridge the gap between these two. So another important here parameter is HDL co-simulation. This feature is basically available in system generator, right? Here you can see that when we are using system generator. HDL co-simulation is basically when we are using system generator, you are designing your system using MATLAB and you are using Simulink and system generator. You are simulating it, right? And you know that whatever we simulate, it doesn't mean that that same thing will be there when we go for hardware implementation. So in order to check whatever simulation we are checking on our screen, same simulation, same output is coming from our hardware also. So in that case, what we can do is we can basically connect our hardware. Here you can see this. This is hardware in loop. This is hardware using either iSIM and model SIM. So here, what will you do? You will design your system, and one part will be based on software-based simulation, means that is coming from your PC. You can monitor that, and another part will come from this hardware FPGA, and that means that output will come from hardware. You can see that window also on your screen, and you can compare both these results, whether simulated output is similar to hardware generated output or not. Only then we can say that whatever simulation we are getting, and same thing we are getting in our hardware also, right? So in this way, basically this hardware simulation works, hardware co-simulation. So here, now I would like to show you one video related to these.
Excuse me, sir.
Okay, this is visible to everyone?
Yes, sir, visible, sir. Particular
Okay.
core simulation.
Okay, let me show one software and its steps. I'm just trying that one. Okay, is it visible? Here you can see that in ISC we are generating code. Here we are generating VHDL if we know the VHDL.
Excuse me, sir.
Yes.
Sir, your PPT screen is only visible, sir.
Only PPT is there.
Sir, HDL core simulation, that PPT slide is only visible, sir.
Okay, so it is not, this screen is not coming.
No, sir.
Okay, okay.
Kindly share again, sir.
Let me check. Still only PPT is there.
Yes, sir.
Okay. Share. Let me share screen again. Now is it okay?
Yes, sir. Now it's visible, sir. The folder.
Okay, okay.
Yes, sir.
Actually, I'm trying one. I want to show one demo of this software. Now it is okay.
Yes, sir. Visible, sir.
Now we are creating project in ISC, right? For front-end VLSI design. So here you have to write the name where you want to save. Now this is the part where you have to select the FPGA. What is the FPGA you want to save? Then go to new source. Here you have to select the library, and then in file name you give file name, and here you have to select the VHDL module. Go to next. And then here you have to give inputs and outputs. Let us say you want to create XOR gate. We are giving XY as input and Z as output. Select it as output, right? So then go to next, finish, yes. And then next, next again, and finish. In that case, you will get this window. Now here you have to write code for your XOR. So we are going to write here Z as output. Z implies, this is the sign for imply X XOR Y. So we are just generating XOR gate. So generate this one and go to check syntax to check the errors if there is any error. So here you will see that in check syntax there should be no error. So green tick means there is no error in your code. Then we are going to do what? We are going to for its simulation. For that, go to test bench waveform generation, generate file, give name. You can give name as test bench for that. Then next, next, and finish. Now you will get this window. Whether you want to generate test bench for a combinational logic or sequential logic, because it is combinational logic. So select combinational and finish. So you will get two windows, two waveforms. Here we are giving first input X, right? And second is this Y. We are just generating a waveform, input waveform from our own side. Then generate the second one, this one. Right. So in this way, you have generated the test bench for XOR gate. So save it, save your test bench, and then go to behavioral simulation. Select from here behavioral simulation and test bench, whatever test bench you have selected. Now here you have to select this simulation behavior model. You can go to its property. You can change if you want to make any changes. Otherwise, it is okay. Then you can change the timings and select from here. So now we are simulating our code, VHDL code, whatever code we have generated. So here you can see that this is the waveform, XOR gate. This is XOR gate. When it is 1 and 0, then output is 1. When it is 0, 0, output is 0. When it is again 0, 1, output is 1. So our simulation is working. So here you can see that it is what it is 1, it is 0. It is 0 and 1, right? So in this way, we can first simulate. So this is the design flow up to what? Code generation, and after code generation, you have to simulate, and after simulation, you have to check its behavior. So this is behavioral simulation, right? So in behavioral simulation, you can easily check it is working as XOR gate, right? So this is up to simulation part. So here you click anywhere. You can zoom in, zoom out in this way. Here, yes. Yeah, here you can see that when input is, this is 1, this is 0, then output is your 1. 1, 0, 1. So in this way, you can check XOR gate. When it is 0, 0, your output is 0. Fine. So this is our coding and simulation part, up to coding and its simulation. Then for its hardware implementation, as I was telling all of you that hardware implementation means you are going to generate the bit stream, and this is the it's so what we are doing now, again we are selecting that same, and in this case you have to select the floor planning. You have to now give actual pin numbers of your FPGA to your X and Y. We have selected their XY as input and Z as output. So here now you have to give pin numbers, exact FPGA pin numbers, only then it will work on hardware, whatever hardware I have shown to you, right? And this is your output. So these are the inputs and this is the output on FPGA. Save it and cross it, right? So after that we have to go for our generate programming file. Generate programming file is nothing but it is bit stream. So we are going to generate programming file. So it is in process. Here you can see that. So our synthesis part is done. Synthesis. Now we are going for implementation. As I told you, now next step is generate programming file. So here you can see that three things: translate, map, place, and route. I have already explained to you, all of you, about this, right? And So once your bit stream is generated, now green click is here. Now here you can see the web talks and process this thing. Before configuring your target device, before configuring your FPGA board should be on. So before clicking this one, your FPGA board should be on. And here you can see that automatically connect to your cable. Now you're connecting, and now your this is the bit stream file generated by the software, and you can ignore this one, ignore, and now you have to program. First is this is your FPGA, right click, program, and your bit stream, and you can see that program succeeded. Once this message is there on your screen, then you can check that hardware by making that toggle switch on and off. So this is the first you can say a demo of ISC. Another example I gave you of hardware co-simulation. That example I can show you here in this one. What is hardware co-simulation actually? So here you can see that as I told you, hardware co-simulation means we have to verify whether our software generated output is similar to our hardware generated output or not. So here you can see that these are your what? These are system generator blocks. This is you can see that system generator block. This is system generator block, and these this input source and these output source we have taken from Simulink. So we are basically here you can see that this is gateway in, this is gateway out. Gateway in is used to convert your floating point out this input into fixed point input. Means it is going to convert it into 16-bit data or 32-bit data, then it will be processed. And gateway output again, it is going to convert your fixed point data into floating point data, and that will be sent to these displays. This is scope 1. Scope, this is scope 1, scope 2. So this top part is basically this top part is software simulated part, and this one is hardware HW COSIM. You can see that this part is your FPGA part. All these things are implemented in this FPGA. So this scope is going to show you the simulated part from this you can say in the software. And this scope 1, it is going to show you the output of your hardware. And now we are just going to check scope 2. It is used to check the software generated output and hardware generated output, whether both are similar to each other or not, or is there any difference. So this is the brief idea about your this circuit. Now we are going to simulate it. We will just check it, how it works. Initially, our FPGA board is off. So whenever I'm going to start its simulation, then you will see that when I run its simulation, because our hardware is not connected, or you can say it is not on, that is why we will get some error of cable that you will see soon. Here, I am going to make it on. Start simulation. So our simulation is starting. Here you can see that initial JTAG hardware co-simulation we are starting, and we are getting error opening programming cable, error reported. So it means that our hardware is not on. So we have to be sure, make sure that our hardware is on before this one. So now we have made our hardware on, and after making our hardware on, again we are starting this simulation. You can see that simulation is starting, and all the scopes are there. Scope 1, scope 1, scope 2. Scope is software generated, scope 1 is hardware generated, and scope 2 is comparison of both. So this green is comparison basically. So here you can see that this is the comparison, and this is scope 1, this is coming from hardware. So this is, you can see that this is low pass filter, right? And this scope is coming from software. So you can see that red one is coming from software, this blue one is coming from hardware, and this green one is the comparison of both. So you can see that both this green color means that both are similar to each other, both are overlapping with each other. That is why it is complete green color. Here you can see that blue, where blue and red is meeting, there it is green. So this red and blue is meeting, that is why it is. So you can say that software generated output is similar to hardware generated output. Now I have switched off the board again. So after switching off the board, my output is gone. This hardware generated output is gone, or here only software generated output was there. So this is one example of hardware co-simulation. To give exposure to our participants, this means how to compare our output generated from software with output generated from hardware. I think from here it will be more clear to all the participants about the this one about hardware co-simulation. So now we will move ahead after these two examples. Now my PPT is visible. Anyone can reply. PPT is visible? Yes.
Yes, sir.
Now it is visible PPT?
Yes, sir, visible, sir.
Okay. Now, after giving the idea about front-end VLSI design and its actual implementation in software using ISC and our system generator, now we are going to discuss the back-end VLSI design flow. What is back-end VLSI design flow? Again, in backend VLSI design flow, there are three options. One is schematic design. Schematic design is nothing but it is again graphical, you can say, representation of your circuit in the form of transistor, gates, modules, etc. You will get in this one. And HDL code again, textual description of your circuit, and it can be VHDL or Verilog. And layout design is basically you are working in what? You are working in physical domain. Now you should be clear from this one. Initially, I told you about the three domains of working. Physical domain, structural domain, and your behavioral domain. So working in this one, schematic design, is your behavioral domain. Working in HDL code, schematic design means structural domain. HDL code means behavioral domain. Layout design means you are working in physical domain. In this case, basically, you are going to design your own transistors, own gates, own modules, and for that you should be very clear about the physical, you can say, parameters of your transistor, your PMOS, NMOS, your gate size. So accordingly, now you are going to create those designs on your silicon area, right? So that is your physical domain. Now, first is your schematic design. As I told you, schematic design is nothing but it is graphical representation or in the form of symbols. Here you can see that if we are talking about this, you can say that schematic design. In this case, actually, I have taken this example from microwind software. As I told you, there are a number of softwares. Yes, Karthik, you have any query? You have raised the hand. Karthik. Okay. So actually, there are a number of softwares for backend VLSI design. As I told you, like Cadence is there, Mentor Graphics is there, Synopsys is there, Microwind is there, Tanner is there. So this diagram is taken from Tanner, from Microwind. And at the end of this explanation, I will give exposure of, or you can say, software exposure of Microwind. So that all of you will get idea, means how we proceed for our backend VLSI design using these different softwares. More or less, steps remain same or flow remain same. Some basically some steps are here or there in different softwares, and with the additional you can say features of vendors, we can work on these softwares easily. So first is, if I'm working on, in behavioral domain, if I'm working in in structural domain, then I have to design my circuit using symbols. So I have taken here two transistors. You can see that this is PMOS, this is NMOS. This I have used for input, to give input to my these two transistors on their gates, and this is the output. So here you can say that this is, what is this? This is inverter circuit, small circuit. So what will be the step? So I am basically using this inverter circuit, and then the next step is, I have started in a structural domain, but now the next step is I am basically going to convert this structure into a SPICE file or deck file, you can say that, where you are going to convert or you are going to mention actual dimensions of your transistors. Here you can see that it is showing NMOS. NMOS, VSS, input to output, and what is the size, length and width of your transistor. Again PMOS, length and width of, so physical dimensions we are mentioning here. So your structural structure, it will be converted into this deck file, and it is in Verilog form. So most of the vendors, they use Verilog file for generating the layout, like layout of physical you can say parameters, and some vendors are also using these days VHDL files, right? So here my first step is I am converting my structural into structural into textural, HDL. So this is basically netlist. Netlist means their connection also. After that, I generate layout. So this is the third domain, that is physical domain. Here, from that net list file or from deck file, my software is going to generate this layout. Here you can see that in this layout, what we are seeing here, top one, these are your PMOS transistor. Down one is your NMOS, and a red color is gate. Here, from here you can see that P diffusion is this color. This is P diffusion, P, and this is your N well. This one N well. This is N diffusion is green color. Polysilicon is your gate. Red color is your gate, and blue color is metal 1. Here only metal 1 is used, and dark blue color is metal 2, but metal 2 is not used because it is on one layer only. So this basically layout will be generated on your silicon area, and this is nothing but this is your complete what? This is your inverter. Right. So now here I would like to give you one exposure about this one. How we can work in 3 domains. So as I told you, we have the option, some vendors, they provide complete solution from front end to back end, right? So whenever basically now it also depends upon how much flexible you are, how and in which basically algorithm you are working at which place you are working for your research part. So let us say, as I told you, when we start this one, either I can go with structural domain, or I can go with behavioral domain, or I can go with straight away physical domain. Structural domain is already explained to you. You can create your structure. This one, this domain, behavioral domain. As you all are aware that from our this MATLAB or HDL code generator, we can generate our VHDL or Verilog code. If you have that code, Verilog or VHDL code with you, straight away we can work on this HDL netlist. We can take that one and we can start our design, right? So in that way, in that case, what we are doing, we are working in which domain? We are working in our now textural domain, right? So, but yes, one vendor to another vendor, compatibility of these things changes. So only if I'm working in like Cadence ports every domain. So we can straight away, we can take HDL file and we can go for its layout generation. MATLAB also generating VHDL code. And in case of Mentor graphics, we can take that VHDL code, but some backend design, they only support Verilog. But some, they are also supporting VHDL. So you have to be very sure means which file is required. You can take that particular file from the MATLAB. And that file from MATLAB means whether VHDL is required or Verilog is required. You can select those, right? And then you can work on them. So in this way, I will take this one and I will make it as deck file. From that deck file, we will get this physical dimension of each and every transistor, or if it is gate or metallization. Metallization is nothing but we call them as conductors, right? Then next step is same, we can generate this layout. And third part is basically directly we can work on this layout part. At present, we have generated it. We have generated it from where? From structural. In structural, I have designed inverter. From that inverter, I have designed its deck file. From deck file, I have generated this layout. Now, and in second part, we have generated this layout from only deck file. In third part, we don't have its structural, we don't have its deck file. We are going to start here straight away. Fine. So there are three methods. One is auto-generated. One is fully custom. Another one is semi-custom. And auto-generation is already explained. This is auto-generation only. Another one is semi-custom and the fully custom, third one. Fully custom is, you can say, fully optimized. You can optimize each and everything from your own side. Here, you don't have any optimization. You don't have optimization in placement. You don't have optimization in routing. Each and everything was auto-generated. So you have less flexibility in this case. Now I am going to discuss semi, right? First, semi-custom or semi-automatic, we can say semi-automatic. In that case, what I am going to do, I am going to take transistor layout from here straight away. And I will place that transistor layout for PMOS, transistor layout for NMOS, and then I am going to make the connection between them, right? And I am going to complete my inverter. So it is basically semi-automatic or semi-custom because I am taking the already present transistor in the library. I'm just taking those transistors and placing them. You can see that now placement is from your side. So you have the flexibility. You can optimize the placement part, right? And now after placement, you are making the connection, interconnection between them. So it means that routing is also from your side. So both the things are from your side. You are placing yourself, you are writing yourself. It means that it is flexible. You have more options. You can optimize your design at your own. So you can play in placement and routing, and you can optimize your design better way. right? This is your semi, you can say custom or semi-automatic. Third is your fully custom. Fully custom means you are going to start with scratch. Nothing is there in your hand. You are going to start with scratch. You are going to create each and everything from your own side. Nothing is there. Nothing prefabricated thing is there. So in that case, what you are going to do, you should be very clear about lambda rules, right? Even in case of your placement and routing also, lambda rules play a very important role. You have to follow the lambda rules. Only then you will be able to make your routing 100%. Otherwise, it is going to give error, right? So you should be very clear about the lambda rules. And when we are going for fully custom, in that case, now you are going to create your own transistor. You will create your own PMOS, you will create your own NMOS, and then you can save them in the library. So here you are not using transistors from the library. You are using, what you are doing, you are creating your own transistors. It means that it is more optimized. You are making your own transistors. Even you are not taking transistors from the library. You cannot optimize the device also. So that is also very big parameter. I am telling you, if you are working on transistor only, single transistor or device, even then you can do your PhD in that particular area only, just one transistor. If you are working in placement, that is more than sufficient. If you are working in routing, that is also more than sufficient. So this fully custom, by having exposure of all the lambda rules, you are creating your own transistor. You are creating PMOS, you are creating NMOS, you are saving in the library. Now you are going to layout. In layout, you are not taking anything. You are taking your own transistor PMOS, you are taking your own NMOS. Now you are making interconnection between these transistors. You are giving them VCC, you are giving them VDD, right? Ground and VCC. Sorry, yes. And now after that you are simulating them. That is fully custom, fully optimized. So you can see that you can choose any one out of these three options. Fully automatic means it will be fast. You can design it in very short time, but less flexible. Optimization possibility will be less. In case of semi-custom, it will be faster than fully custom, but it will be slower than your automatic. But it will be more flexible than automatic and less flexible than fully custom. And in case of fully custom, it will be slow as compared to both, but it will be more optimized as compared to both. So you can optimize everything, area, speed, power, everything you can optimize in case of fully custom. So depending upon the time, depending upon the cost, and depending upon your requirement, you can choose any one of these options and you can go ahead with your VLSI design. So with this, I can give you its now exposure to all of you, how we can do our what will be the flow of this software in microwind. So here you can see that I will give just one example of so is it visible now?
Yes, sir, visible, sir.
Okay, I'm going to show the basically demo of microwind software. So we are going to start with this one. Here you can see that this is DSCH environment, and I'm going to design one inverter. Here I have selected PMOS. Now I have selected NMOS. After that we can select This is ground. Give ground. This is VDD. Now I am selecting output, LED as output to check my output, and I am selecting here input. So here you can see that I am placing all these components, and now you have to make the connection between them. We are making connection here. Now clock is there. I am going to just give this connection. Connect clock with both the gates of NMOS and PMOS. Now run simulation. Sorry, one connection is left. This ground is also we have to connect. Yes. Now run simulation. Select run simulation, and you will see, because we have selected clock, it is making on off because of this clock. When clock is high, then it is low. When clock is low, then high. Then you can just, this is the simulation of your, and we can save it as inverter 1, or we can give any name. Now we have selected it as inverter 2. Save. Right. Then we can this is the Verilog file. You have generated that file, spice file, as I told you, right? Now, then we have to go to generator part. Here we have to generate the layout. Here you can see the different layers. Compile, go to compile, compile Verilog file, select that Verilog file, inverter 2 by inverter 2. Yeah, this one, this is the file. Open. So here it is going to, now we are going to select generate, and you will get the layout of our inverter. Now this is automatic generation of our inverter layout, right? So our inverter is generated. Now we have different simulations in this point. We can simulate our inverter. Here you can see that when it is high, then output go low. Hey, when it is low, output is high, right? So it is working just like our inverter. So this is basically SPICE simulation. Here we are considering each and every parameter of the transistor in this simulation. But in earlier information simulations, we are bothered about the you can say low and high. Here we are going to calculate each and everything, RC delay kind of things, right? So different simulations you will get here. Here you can see that this is analog simulation. We call them as analog simulations, and various options are there, and you can simulate your design. So this is the example, first example. Here you can see that it is showing you the delay, right? And its power consumption. And this is one example of your auto-generated, fully automatic design. From your schematic to we are generating SPICE file, and from SPICE file now we are generating this layout. So in this way you can generate your layout for ASIC design. Right. So this is the exposure of microevent software for designing your layout. And now Now PPT is visible.
Yes, sir, visible, sir.
PPT is visible now.
Yes, sir, PPT visible, sir.
Okay, now we are going to conclude. From this complete session, we can say that VLSI designer may select any one of the two, whether it is front-end design or back-end design, depending upon the availability of inputs. So many inputs are there, and majority of the inputs are your software and hardware. So if these are major basically things, if you don't have the relevant or required software or hardware, you will not be able to complete your project or design. So with this, now I stop here. And these are some references for this session. First is CMOS VLSI design by Veste, then modern VLSI design by Wayne Wolf, then FPGA based system design by Wayne Wolf, user manual Xilinx ISC, user manual Xilinx system generator, user manual XLDSP, lecture notes, university programs, Xilinx university program. And with this, thank you very much for patience listening to all of you. Now I'm just keeping this session open for queries.
Dear participants, if you have any doubts or queries, you can ask now.
If any of the participants, they have any query, you can
So there is one question in chat box, sir. Give the difference between Xilinx simulation and microwind other than open source.
okay. And now am I audible?
Yes, sir, audible, sir.
Okay, your question is the difference between ISC simulator and microwind simulator. What is the question? Okay. The difference between Xilinx simulator, basically Xilinx simulator is used for front-end design and microwind simulator is used for back-end design, right? This is the basic and main difference between two. Any other query? Or you can write your query in chat also. Any other query from any other participants? If you have any query, please go ahead.
Sir, there is no more queries from participant side, sir.
Okay, if there is no more query, then I'm really thankful to the organizers of this program for inviting me to share my experience with all of you. And I'm really thankful to the organizers and to all the participants for their patience listening. Thank you. Thank you very much.
Sir, let me conclude the session, sir. Kind words are short and easy to speak, but the echoes are truly endless. In this way, I would like to thank our today's resource person, Dr. Rajesh Mehra, Professor and Head, Department of CDC, NITT or Chandigarh, for providing a wonderful session in the topic of VLSI design flow. On behalf of organizing team, we once again thank you, sir.
Okay, thank you. Thank you very much. Shall I leave?
Thank you, sir. Yes, sir, you can leave, sir.
Okay,
Thank
right.
you, sir.
Thank you.
Dear participants, the day 1 session 2 attendance and the feedback link is posted in chat box. It will be open up to 30 minutes only, so kindly fill it soon. Thank you all.